Here's another kind of question they really like to ask when they want you to combine trig identities and complex numbers together. So we've got 16 times sine to the power 5 theta, and that's equal to this expression here. And it looks very similar to this in some sense, but here we've got 3 theta as the argument, whereas here, just to make that really clear, that's to the power 5 here, and the theta is the argument there, right? And I'm not too sure how much information they always give you, but this is something that you will need to solve this, and we've looked at this property before. And remember, this is when z is equal to cos theta plus I sine theta. There, this property is true, right? So how can we sort of use this to help solve the problem? I guess things I'm thinking of are, okay, well, this has the power 5 here, so I'm going to have to incorporate that in some sense. And then I look at these kind of coefficients and I'm thinking, these are kind of familiar, right? So I'm trying again, think about combining the Moivres and the binomial expansions to see what I can do there. Let's look at this case, for example. If we just took z to the power 1, right, I could have this property here, but then I can also think about, okay, but I want to incorporate to the power 5 here with that just single theta of an argument. I don't want to change the argument at all. So what I could do is, if I raise both sides to the power 5, now this is something that I could do. That would give me, looks like 32 minus, 32i sine theta to the power 5. Okay, so I mean that's something, and it looks something like this. So again, I think I'm sort of heading in the right direction, but then I want to think of how can I get this expansion out over here? And that's what we want to think about, is there another way that we could write this, right? Something to the power 5, how else can you write that? Well, again, think about your binomial expansions, right? So I could say z to the 1 minus z to the negative 1 to the power 5 is also equal to, and let's write out my coefficients here. I might need a bit more room. So looking at our powers over here, I'm going to have my ascending powers and my descending powers. So let's go z to the 5, z to the 4, z cubed, z squared, z to the power 1. And then I've also got here z to the power 0, z to the power negative 1, z to the power negative 2, z to the power negative 3, and so on and so forth. Okay. Oh, and be careful with these alternating powers here. So the signs do alternate because you've got this negative symbol here. Okay, that looks good to me. And then we can simplify this out a bit more as well. So we've got here, that's just z to the 5 minus, we can simplify these indices a little bit, so that's 5z cubed plus 10z minus 10, that looks like z to the negative 1 plus 5z to the negative 3 minus z to the power negative 5. So at this point, I mean, we've got this long expression here and we've got this expression here. What can we do with these? Well, the idea was that we wanted some sort of trig expression on one of the sides. I mean, we have this, but then where does this kind of come from? Again, thinking about what's going on here, well, if you look at these powers very carefully, you'll actually notice a little pattern that's emerging. We have these positives and then we have these negative components over here that we can actually sort of combine. I'll show you what I mean. So we can actually group these up in a particular way. So z to the 5, take away z to the negative 5. And then I've got here, so I can factorize out a 5. I could factorize out a negative 5 here because I want this written in a particular way. So that's going to be z cubed minus z to the negative 3. And I can factorize out a positive 10 here. So that's z to the 1, take away z to the negative 1. And then actually, if you look very carefully, this is hopefully something familiar, right? Because this is actually the same as this here, but with different n values, right? Oh, sorry, the same as that here, with different n values, right? So I can actually simplify this as when n is equal to 5, right? That's just going to be 2i sine 5 theta Okay, and this is here going to be negative 5 outside of, same thing here, but now with a 3 there, so that's 2I sine 3 theta, plus, same thing here, 10 outside of 2I sine theta. Okay, so far so good. So what I'm going to do now is I've got these two expressions. So you can say this is equation 1, this is equation 2, and we could say over here equating 1 and 2. Right, what have I got? I've got 32I sine 5 theta is equal to 2I sine 5 theta. Let's simplify that. So it's negative 10I sine 3 theta. Oh, there's meant to be a 3 over here. Sorry. Yeah, I was wondering what was going on there. Okay, cool. Sine 3 theta and 20I sine theta. Okay, cool. And then, lo and behold, we got something like this. How can we get to that last step? Well, these i's are in common, so we can divide them through. And then we can also divide everything else by 2. So that's just going to leave me with 16 sine 5 theta is equal to sine 5 theta minus 5 sine 3 theta plus 10 sine theta. And hopefully I've done everything right. I think that's pretty good, except for the 3 theta that I left off earlier. Okay, cool. So that's the idea behind this. We start with something that is involving these trigonometric expressions. But in order to get started with the problem, we have to let our complex numbers equal to a particular expression and use the properties that we're given here to approach this problem to get our final answer for the proof.